So we have been solving problems on divisibility, and this is the next exercise. Here two integers are given, positive integers of course, d and n, such that d divides n. Then we have to prove that 2 to the dth power minus 1 divides 2 to the power n minus 1. And a hint is given. In fact, the hint tells us exactly what we want to do. So let us see the solution. Since d divides n, we have n equal to kd. For some positive integer k. So we have to prove that this is divisible by this number. So we start with this. Then two to the nth power minus 1 is equal to 2 to the power kd minus 1, that is equal to, you can write it as the kth power of 2 to the power d minus 1. So now we can use this formula from elementary algebra with 2 to the power d in place of x. So that will give us this times k minus 2 plus 2 to the power d plus 1. Now this of course is an integer, in fact a positive integer. So from this equation we see that this divides 2 to the power n minus 1. So we write hence this. If you want, you can mention that fact, that since this factor is a positive integer, that's why this divides this. We have chosen not to mention it. Why? Because it is something that starts becoming obvious when you are within number theory. In fact, in any part of mathematics, the deeper you go into that part, the more things you will learn, and the things which were not obvious previously start becoming obvious to you. So you start writing less and less about those things which you find obvious. So you also expect others to find them obvious, and you don't waste time writing such things. That is why parts of advanced mathematics seem somewhat unreadable when one starts a particular part of mathematics. If one immediately jumps to a very advanced portion of that part, one sees that one does not immediately understand almost anything. That is because of that suppression of information, those missing steps. But we are supposed to of course supply those missing steps, because by the time we reach those parts, if we go according to how we are supposed to go, if we reach those parts, by that time we should know those things. Okay, so there is no one absolute way of writing a solution. If you want, you can supply that detail, or if you feel that it is it's an overkill. One should be able to understand that this divisibility demands that this be a positive integer, then you decide to not write it. So that's what we have done. So that is part A. Now you apply that part A here and prove that 31 and 127 divide, both of them divide this integer. Since 5 divides 35, it follows from part A that 31, which is 2 to the power 5 minus 1, divides 2 to the power 35 minus 1. Similarly, (127), which is 2 to the power 7 minus 1, also divides 2 to the power 35 minus 1. So that is the solution. Oh, I seem to have already run out of ink. Give me a moment. Let Tn denote the nth triangular number. For what value of n does Tn divide this sum? The sum of the first n triangular numbers. We have to find those values of n for which Tn would divide this sum. And here also a hint is given. See exercise 1C, part C from exercise 1, from the first section of the first chapter. Of section 1.1 we have this thing 1 times 2 plus 2 times 3 etc. plus n times n plus 1 is equal to n times n plus 1 times n plus 2 divided by 3. For all positive integers n. See that suppression of information or not supplying obvious things as details, that actually determines everything. You see this part for all positive integers n. In the context of these exercises, these problems, we know that whenever we see n, it's almost always a positive integer. That, however, is not necessary unless we explicitly mention what n is. So, to someone who is seeing these things for the first time, they may actually get confused what n is if we don't explicitly write what it is. So, see, that is why sometimes it's good to write things in details, especially for those people who, at this level it does not seem like much, but the deeper we go into number theory, the more you will feel that details are missing, and that you also find in any textbook, in any part of mathematics. The more you go inside that theory, the less details the author is providing, because he or she expects you to know the things. But when, this is something else, when you teach that thing to someone, it's better to supply those details, because if you don't do that and you expect your listeners or your students to know the things, then that's where the gap starts for me. They don't understand it, they struggle. Of course, as learners we have to struggle to some extent, but not to the extent that the things become totally unmanageable and all the things go over our head. So some details should be supplied. Anyway, so exercise 1C from the first section is just this, which there we were asked to prove this using induction. So you can immediately see one thing, that what is the nth triangular number? It is the sum of the first n positive integers, and we also know a closed form expression like this, a more compact formula for this sum. and all these terms look like this thing, except we lack 2 in the denominator. So what we do, in order to create this sum, we divide on both sides by 2. That's it. So t1 plus t2 plus dot 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 tn equals 1 times 2 divided by 2 plus 2 times 3 divided by 2 n times n plus 1 divided by 2. So it is 1/2 of that, n times n plus 1 times n plus 2 divided by 3. Now what we do here, we take n plus 1 and 2 together, so that they give us our tn times n plus 2 divided by 3, tn times n plus 2 divided by 3. Now we want to figure out those n that will make this sum divisible by tn. So that means we are trying to find those n for which this portion is an integer, and that amounts to finding those n for which n plus 2 is divisible by 3. Thus, this is divisible by tn if and only if. It's both ways that follows from this equation. 3 divides n plus 2. So for example, you can take n equal to 1, that will do, because 3 divides 3, and which is something very trivial. When n is 1, this sum is just t1, which of course is divisible by t1, and other values of n will also exist. So that ends the solution. Then (23) exercise. If A divides BC, show that A divides the GCD of A and B times the GCD of A and C. We use the property of GCDs that we know, that the GCD of A and B, for example, is a linear combination of A and B with integer coefficients. There exists integers, say m, n, p, q, such that this greatest common divisor is ma plus nb and the other GCD is pa plus qc. P and Q often denote primes, but we can use them as just some integers. If you want, you can use something else here also, maybe TS. Then what happens if we multiply these two expressions? Multiply the terms out. MPA square plus MQAC NPAB plus NQBC, because ordinary multiplication is a commutative operation, so it does not matter how you write these terms. Since, okay, so you see that there are 4 terms here. The first 3 of them already have a in them, each one of them has a, and the last term has bc, which is divisible by a. So all the terms are divisible by a. So that is why this product is divisible by a. Since a divides bc, it follows from the above calculation that a divides the product of these two greatest common divisors. That ends the solution, and that also ends this set of exercises. The next section involves the Euclidean algorithm, which probably you already know. If you are given two integers, say 12 and 16, okay, let me write them like this. Let us write all the positive divisors of 12 as well as 16. 1, 2, 3, 4, 6 and 12, and those of 16 are 1, 2, 4, 8 and 16. The common positive divisors are 1, 2 and 4. There is no other common divisor, and the largest among those common divisors is 4. So the GCD of 12 and 16 is 4. The greatest common divisor, the greatest among the common divisors. But this, however, is just the definition of the GCD of two integers, at least one of which is non-zero. But this is a I mean, just using the definition, you can of course see that it will quickly become unmanageable. I mean, if two very big integers are given to you, how can you, I mean, you can try to find all its divisors, but that in itself is a very large task. So there should be some way for you to find out the GCD without finding out the common divisors like this. And one such standard way is the Euclidean algorithm, where we use the division algorithm again and again to find the GCD. And that is something probably you already know. So this we will do in the next video. We are ending the video here itself. It's a short one. So in the next number theory video, we will start that next section, which treats this Euclidean algorithm and things related to that. So we will see that. And tomorrow we have, last Saturday we had videos on Galilean's exercises. So tomorrow we will do solve exercises from Abstract Algebra by Gregory T. Lee. And on Sunday we have our analysis as usual. So that will be all for tonight. If you want to say something, you can write in the comment section below, or you can mail me at my usual address. So see you tomorrow with Lee's exercises. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.